Hi guys, so today we're going to talk about limiting and excess reactants. So as you know, we've been talking about s'mores, an analogy for stoichiometry and that balanced chemical equation. And we've been using 2 graham crackers with 1 marshmallow, kind of a demonic looking marshmallow right there, and 3 chocolate pieces is ending up with our s'mores. And this is the chemical formula that we've been using for s'mores. So basically looking at limiting reactants and reactants that are in excess is that we're looking at different numbers or amounts of our reactants coming together and calculating how many s'mores we could make. So for example here, if we have 10 graham crackers and 3 marshmallows and 12 chocolate pieces, how many s'mores can we make? Well, by using our chemical equation down here, we see that we can only make 3 s'mores because we only have 3 marshmallows. So in this scenario, marshmallows would be our limiting reactant. They are determining how much product we're going to end up with, and they are the reactant that will be used up entirely. There won't be anything left over. Meanwhile, we'll have an excessive amount of graham crackers and chocolate pieces. So if we can make 3 s'mores, that means that we're only going to use 6 graham cracker pieces, and we will have 4 left over. And let's see, if we're making 3 s'mores, we will only need 9 chocolate pieces, and we will have 3 pieces left over. Although I would argue that there's no such thing as leftover chocolate, right? But anyway, so this gives you an idea using our s'mores analogy about limiting reactants and reactants that are in excess. So here we go. This is basically the definitions that I just said while using the s'mores analogy. Here's for excess. It's the reactant that is not completely used up. Here's a more chemical representation. Here we have hydrogen and nitrogen put into a sealed container. And if we actually calculate, add up the hydrogens, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I count 15 hydrogens, and we have 5 nitrogens. So if we think about how they come together to make ammonia, we can see that we're going to need 3 hydrogen molecules for every 1 nitrogen. And so when we pair those up, we see that we end up with 2 representatory particles, or 2 moles, as we know the unit of the coefficient is mole, 2 moles of ammonia. So before the reaction and after the reaction. And so we see that using our balanced chemical equation, everything balances out. The atoms that are there in the beginning result in. Here we're continuing to look at hydrogen and nitrogen, but we've taken some of the hydrogen away. So now when we look, we see that we're not going to use up all of the nitrogen. So the nitrogen is in excess, and we see that the hydrogen will get all used up, and so that will be our limiting reactant, and will determine how much ammonia we can make. Let's look at another scenario here. We have our balanced chemical equation up top. For every 2 moles of hydrogen, we'll need 1 mole of oxygen, and that will produce 2 moles of water. Pause the video and take a moment and do your calculations to see how many moles you have of each and how many you will create here at the end. Okay, so here we counted our representatory hydrogen moles here, and we see that there are 10, so that means we have 10 moles of hydrogen. And here we count 1, 2, 3 to represent 3 moles of oxygen. And if we bring them together, we would be able to make 6 moles of water. And that means that oxygen is our limiting reactant, hydrogen is our excess reactant, and it's going to have 4 moles of hydrogen left over, along with those 6 moles of water that we can make. So basically how you do this is for each reactant, you calculate the amount of product formed, and the smaller answer indicates which one is going to be limiting. So here we have an example. Let's consider hydrogen gas and chlorine gas coming together to form 2 moles of hydrochloric acid. So how many moles of hydrochloric acid will be produced if 5 moles of hydrogen react with 4 moles of chlorine? Now this one's easy because we see that our ratio is 1 to 1. So we know that moles of chlorine is going to be limiting because we don't have 5 moles. So we're going to have a whole extra mole of hydrogen left over there. But let's say it wasn't this easy and we needed to actually do our calculation. So we would use our stoichiometry here. So we would start with 4 moles, sorry about how messy that is, of chlorine. And we would do our conversion from moles of chlorine to moles of hydrogen. And we would pull that from our balanced chemical equation. So we have 1 mole of chlorine on the bottom, and we have 2 moles up top. And we see that we can make, oh, so hard to write with the little pencil here, 4 times 2, we can make 8 moles of hydrochloric acid. And if we were using those 5 moles of hydrogen, which right now I know you're like, why are you writing this out? It's so easy to see, because it's not always easy to see. And so we're making sure that we know how to do this in any situation. And so here this time we're going to use the hydrogen ratio with our product. We don't need to convert to grams. We're staying in moles the whole time. So this is 1 mole of hydrogen to 2 moles of HCl. And so there we can see that it would be 5 times 2 would mean 10 moles. And remember that whichever one is the smallest one is the amount of product we can actually produce, and the larger one will be in excess. So we can only produce 8 moles of HCl, and hydrogen will be in excess. Let's look at another one. Okay, so here we have carbon dioxide and oxygen, carbon monoxide and oxygen forming carbon dioxide. So we want to know how many moles of carbon dioxide will be produced if there's 12 moles of carbon dioxide and 7 moles of oxygen. So we can why don't you try writing this out and come back and see the answer. Okay, so hopefully you tried that on your own. Part of it was I didn't want you to have to sit there while I wrote this out. It takes so long. So 12 moles of carbon monoxide is what we're starting with, and we pull that ratio from our equation. So we have for every 2 moles of carbon monoxide, we're going to make 2 moles of carbon dioxide, which means we're going to end up with a total of 12 moles of carbon dioxide. But if we have 7 moles of oxygen, and that one is a 1 mole of oxygen, will produce 2 moles of carbon dioxide. With the 7 moles of oxygen, we end up with 14 moles of carbon dioxide. So that means that carbon monoxide is our limiting reactant and is going to determine that the most we can make is 12 moles of carbon dioxide. All right, here we have aluminum reacting with chlorine gas, producing aluminum chloride. But this time, we're starting with a mass. We have 100 grams of aluminum and 100 grams of chlorine. So that means you need to do your conversion from grams to moles and then use the mole ratio from the equation. Give it a try and come on back. Okay, so here's this problem worked out. We can see our conversion of aluminum from grams to moles using the molar mass, and then the conversion of moles of aluminum to aluminum chloride using the mole ratio from the balanced chemical equation. And this is how many moles of product we would get if we started with 100 grams of aluminum. But if we start with 100 grams of chlorine, we convert that to moles of chlorine. Then we use the mole ratio from the equation again, so 3 moles of chlorine results 2 moles of aluminum chloride. So we use that mole ratio, and we see that the only product we can make from 100 grams of chlorine is a little under 1 mole, 0.94 moles of aluminum chloride. And so this means that chlorine is our limiting reactant, and aluminum will be in excess. And the most aluminum chloride we can make here is 0.94 moles. Well, what we can do is we can figure out how much aluminum we actually need so that we don't waste all that extra aluminum. And so what we can do is we can take that product, that limited product, and bring it down here. And we can convert moles of aluminum chloride into moles of aluminum, our excess reactant, and then convert that to grams of aluminum, and that tells us that we really only need 25.37 grams of aluminum, which means that we have an excess of 74.63 grams because we subtract that number from our original 100. So that would be a huge waste if we just dumped 100 grams of aluminum with 100 grams of chlorine there. Here's our last example. Pause the video and give it a try and then come back to see the answer. Okay, so here we are with our answer. We have the 50 grams of hydrogen. We convert grams to moles, use our mole ratio from the equation. Now this one is asking us for how many grams of the product we'll produce, so we have to go from moles of product to grams. And we find that 50 grams of hydrogen will produce 450 grams of water. Whereas if we have 100 grams of oxygen following the same process, the only difference is the molar mass of oxygen and the ratio of how many moles of oxygen are needed to produce the moles of product. And we find there that we have 112.5 grams of water, which, by the way, if we go by sig figs, we see there that we only have 3 sig figs, and so that should be 113 grams of water, right? And so oxygen is limiting, hydrogen is in excess, and we can only make about 13 grams of water, or 112.5. You can also use that number to reverse the equation for hydrogen to figure out how much hydrogen we actually need, right? So we would take that 112.5 grams and plug it in and do the reverse here to get us to how many grams of hydrogen we actually need. All right, so hope you enjoyed limiting and excess reactants.